The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis.
The force is stressed.
At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
So you can see it necking right now. It's getting thinner right there.
In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test,
we're gonna stop there. So the key things I want you to take from this is that as you pull in a tensile strength test for a material, you put the cylinder material into the tensometer, and you pull on it. The higher, like the force, the larger the amount of force measured. So force here is P divided by surface area. That's the stress. So the higher the force per surface area that you pull on the object with, it's going to cause the material to stretch out in a uniform way in the beginning and in an elastic way in the beginning. Meaning that if you let go of the force, if you stop applying the force, the material will bounce back to its original length. You can see that part of the graph, which is in the first part, and it is a straight line, and it is called elastic here. So I might ask you on a test which part is elastic. You would have to need to know that's part of that is the straight line, the linear part of this graph. There comes a point in the test though where if you exert a certain level of force per surface area, a certain stress on the object that is enough, it's going to permanently deform. It's not going to bounce back to its original to its original length. And if you continue to apply more and more and more force, it's going to reach a point where it begins to neck, where it starts to get skinnier at one particular part along the length of the material. At that point, all of the additional force you apply is going to cause that material to stretch only at the neck. All of the stretching is going to happen at the neck, and it's going to continue to stretch and become thinner until it fractures and breaks. Any part of the graph that is over here is referred to as plastic. Plastic just means it has changed and it will not bounce back. Okay, so kind of key points to note. Y-axis is stress, defined as force over surface area. Strain is represented by a variable E, which is computed as basically a percentage change in the length of the object. That is on the x-axis. First part of the graph is elastic, meaning it's going to bounce back. Second part of the graph over here is plastic, meaning it is permanently deformed and will not bounce back. The high point here is going to be the point at which it starts to neck, and the part at the end is the point at which it fractures. Okay, those are the key points in the graph. I'm going to hope that you can explain those to me as a way of representing what happens to a material when you do a tensile strength test and you apply a stress force to it. What happens to the length of the material or the strain? Okay, engineering stress. They got into a few other calculations in that video that we're not going to need to know. I am going to expect that you will be able to apply this. If I give you stress and force, I would expect you to be able to tell me what the surface area is. If I gave you force and surface area, I would expect you to be able to tell me what is the stress. So if I give you any two of these things, whether it's stress or force or surface area, I would expect you to be able to calculate the third. It's just simple division. Similar thing with strain. If I tell you strain here, the engineering strain, it does not have a unit. It's basically a percentage change. If I gave you the strain and gave you the original length, L naught, I would expect you to be able to tell me what the current length is of the material. Or if I gave you the current length and what its starting length was in the test, I would expect you to be able to tell me what is the engineering strain at that moment during the test. Okay? Again, pretty straightforward math. I would expect you to be able to tell me what the elastic region of the graph is compared to the plastic region. Elastic, the part where it bounces back. Plastic, meaning it's permanently deformed and it's not coming back to its original length. Okay, we talked about it here. Same graph, same idea. Okay. Additionally, so the whole point of a tensile strength test is to measure the tensile strength of a specific material, right? And so every type of material, whether it's copper or gold or silver or a different alloy, a blend of different materials, they will have its own level of tensile strength, right? That's one of the things that's different from material to material. And so when scientists measure the strength of the tensile strength of a material, they have figured out they've measured the stress, which we would have just measured. They've measured the strain, how much it stretches, and for every material there exists something called the modulus of elasticity, which here is a capital E. And so what ultimately scientists are trying to figure out when they do the tensile strength test is what is this capital E? What is the modulus of elasticity? It's another way of saying how much does it stretch when I pull on it? That is what they are ultimately trying to calculate for each material, is this capital E, okay? So the test itself lets you figure out what the stress is and what the strain is. Ultimately, what you're trying to figure out is what is the modulus of elasticity, what is that capital E for a particular material, okay? And it's different for every single material. So hopefully that all makes sense, and when you have questions about it, please ask me about it, okay? That we mentioned, I mentioned, and in the video they mentioned the yield point in a material during the tensile strength test, and so it's the point at which the straight part of the graph begins to curve. That lets you know how much force per surface area, so how much stress you have to put on a material of a specific kind in order to make it permanently deformed, to go from that elastic part of the graph to the plastic part of the graph, to the part where it's permanently deformed and it's not coming back. Okay, yield point Y, it's just a way of saying what's the yield point, and it's important for every material because if you're like designing something, right, you need to know how much force can it withstand before it permanently changes shape. It's super important when you think about anything metal that you're designing. What is the yield point? What's the strength? What's the yield strength of that material? Okay. This is just another way of saying the same thing. In the very beginning, in the elastic part of the graph, in this part right here, the straight linear part of it, you can figure out how long a material, if you know the the modulus of elasticity, and you know, for instance, how much strain you're putting on it, how much stress you're putting on it, you can figure out what the strain would be, right? That just makes sense. Like if you know what this E is and you know how much you're pulling on it, you'd be able to figure out how much it can stretch before it pops back. This is called Hooke's law. This only applies to a material when it's during the elastic portion of the graph. It only matters if it hasn't gotten to that point where it's permanently deformed. Once it's permanently deformed, this law does not apply anymore and it doesn't matter, okay? Yeah, we're going to skip that. I'm going to skip some of this other stuff. It's kind of repetitive at this point. So that's it. The tensile strength test, showing with the stress strain curve that is shown here, it's one of the most typical ways of measuring the strength of a material. It's easy to perform the test. It's easy to get the samples of the material, and it is a very quick, easy way of figuring out how strong that material is. And so the tensile strength test is very commonly performed on materials to see how strong they are. The exact opposite of the tensile strength test is a compression test. Instead of pulling at the top and pulling at the bottom and see how much you can pull it, how much force you have to pull it apart before it starts to bend, before it becomes permanently deformed, before you reach that yield point. Compression test is the opposite. You're squishing it. You're pushing down on the top and pushing up on the bottom, and you're seeing how much force you have to push on something before it kind of permanently squishes. So it's kind of the exact opposite. If you start off with a material of a certain height, right, and you start to squish on it, push down on the top and push up on the bottom, it's going to get shorter, and it's going to get a little bit fatter in terms of its cross-section surface area. Right? Just makes sense, right? It's like if you imagine just squishing on for instance, squishing on a basketball or something, right? Like if you squish on the top, push up on the bottom, it's going to get a little bit fatter and it's going to get shorter. Same thing happens with metal, it's just harder to see. But it's the exact same concept. The compression test works exactly the opposite of the tensile strength test. And you can see what happens. You put the material in the middle, you push down, you push down on the top, push up on the bottom, and it gets fatter and shorter. Okay, cool. That's it. The math is also very similar if you're trying to figure out the stress on the object. It's going to be force divided by surface area. So the stress is force, how many pounds or newtons of force you're applying to it, divided by surface area. And the strain, instead of getting longer, it's getting shorter, right? So the height is getting lower. So here, H naught is your original height. H naught is your original height. H is your height of the material at any point during the test. So say your original material was, again, it started off, say it was 10 millimeters. And now midway through the test or whatever, say it's down to 8. The height is now 8. So in this case, you would take 8 minus 10 and divide it by 10. And so you'd end up with 8 minus 10 is a negative 2 over 10. So it's negative 0.2. So in a compression test, the strain is a negative value because you're getting shorter. So it's getting smaller. It's still, though, it's like a percentage change of the original height. Okay? But it's just a negative sign because it's getting shorter. You could do a tensile strength test and a compression test for any given material, but very often, because when they actually do the test, the values they get for the modulus of elasticity, it's about the same amount of force you have to press or pull on the object to get it to permanently deform. They very often just take the tensile strength test and use that for a compression test value as well. Okay, that's about it. When you're taking the quiz, make sure that you understand stress, what it means, and how to calculate it. Make sure you understand what strain is and how to calculate it, both for a tensile strength test and for a compression test. It's pretty simple math, but you need to be able to do it. Make sure you can interpret the graph and explain what different parts of the graph are telling you about a material. Make sure you understand Hooke's law. Understand that you can explain what the modulus of elasticity is. Make sure you can explain how the tests are performed, what happens to the material in terms of its shape when it undergoes the test, either the tensile strength test or the compression test. We were measuring what happened to the materials. This is kind of what happens to material during the compression. Squishes, a little bit fatter. That's it. I love watching these videos. Anyway, that's about it. All right. Poor Thomas. Anyway, outro video here.